All right, so here we're going to get into this next section of proving trigonometric identities. This ends up being just things that look a little more complex. We're going to need some bigger tools for this and a little bit more foresight about what's going on to prove some of these trig identities. But we are now in the guts of this, with what ends up being kind of one of the most demanding parts of this course is getting some practice done with this. One of the things that students find difficult about this is that at times you feel like you have no direction. You have no idea where to go with this. And when you can't get the left side and the right side equal to each other, then what do you do? But this list of strategies that we've been compiling should help. Starting off with work with a more complex looking side. Number two, keep your eyes on the prize. Keep looking at, keep in mind what's going on the other side of the equation. That's what you're aiming for. Turning things into sine and cosine, using Pythagorean identities, using the fact that we'll need a lowest common denominator if you're adding or subtracting two rational expressions. Using a conjugate is closely tied into that sometimes. And we'll get into some other stuff in this section also too. So let's start off with this one. We have secant to the 4 minus 1 over tangent squared. On our right side, we have secant squared theta. That's 1. And just immediately, it's not really obvious what we're going to do, how these are going to be equal to each other first, but maybe this would be a good time to introduce strategy number 7. And sometimes 7 is, if we can factor some pieces, then we can often simplify those and divide them out. And so if there's stuff to factor in here, that's often going to be something that we're using. The fact that we have secant to the 4 minus 1 is a difference of squares. This is equal to secant squared theta plus 1 times secant squared theta minus 1 all over 10 squared theta. We are starting with the more complicated looking side, so the left side. At this point, hopefully we remember that we have Pythagorean identities that might be relevant here. And if you don't quite remember which one to use, sine theta plus cos theta, or I suppose the other day I wrote it the other way around. It doesn't really matter because it's just adding. Sine squared plus cos squared is equal to 1. Here in the denominator, we've got tan squared theta. And so if I divide each of those by cos squared theta, we come up with your second trig identity. And this ends up being tan squared theta plus 1 is equal to secant squared theta. And so therefore, by subtracting tan squared theta, it's equal to secant squared theta minus 1. So that denominator and that numerator actually are going to divide out. Hopefully, we would have, that should have triggered something in our memory about secant squared minus 1 and tangent, and that those are all interrelated. If you don't remember how this rule goes, one of two things. You can either derive it like we just did here, or it's on your formula sheet for this course. Either way, this ends up being secant squared theta plus 1 tan theta over tan squared theta. And those will divide away. Simplifies quite nicely. Right side. Left side equals right side, QED, or a blank circle, or a blank square, sorry. Restrictions, because we have tangent in the denominator and tangent can't equal 0, so therefore if we have 1 over tan squared theta, therefore sine squared theta can't equal 0. We also have cos squared theta can't equal 0 because tangent is present in this formula. Secant is 1 over sine squared theta. So for those reasons, sine and tan squared, neither of them can equal 0. So therefore, our bad points are all of those. Therefore, theta is not allowed to equal pi over 2. But this over here on the left side is all of our stuff. On the left side is all of our proof. This right side here, this is our restrictions that we need to look at each time. And there it is. Okay. Next one. Our left side. It's like 1 over 1 plus sine theta. Not really pretty. Maybe we'd work with that. Except the right side looks like even worse. So secant theta minus sine theta, secant theta. So let's work with the right side. Strategy number 7, like we just said in the last question, is to factor. If there's stuff that we can factor away, so we can hopefully divide stuff out. Therefore, we can come and factor a factor of secant theta. Leaves me behind with 1 minus sine theta over cos theta. Now, here's what I mean by keeping an eye on the other side. And so we have 1 plus sine theta over on the left. We have 1 minus sine theta in the numerator on the right. They're not exactly the same, but maybe that gives us, foreshadows some clue of what's about to happen. The fact that secant is 1 over cosine means this is 1 over sine theta over cos squared theta. Well, hopefully you see what I did with that. That secant is 1 over cos. Cosine in the denominator multiplied by the other cosine in the denominator. And now, you see, cos squared is 1 minus sine squared. 1 minus sine squared, keeping an eye on what this is 1 minus sine theta, 1 plus sine theta. So factoring it into its conjugates, that's going to divide away. And then that's equal to 1 over 1 plus sine theta. Equals left side. Therefore, left side equals right side. QED. What can x not equal? Because of our denominators. Sine theta cannot equal plus or minus 1. Whether you notice that there's cos in the denominator, or whether you notice that sine squared or sine theta can't equal plus or minus 1, it really just ends up being all of those points and pi over 2. And that is it. So, again, lots going on in these questions. This third one isn't too bad. Maybe hit pause for a minute and see what you can do. I'll catch up to you when you start going again. All right, so hopefully give that a shot. left side is tan x cos x over cosecant x. The right side is just 1 minus cos squared x. So maybe we're seeing where we're going with that. We could probably just convert that to sine squared x before we get very far with this, just to see what we're aiming at. Tangent is sine over cos. Well, we can write it like this. We can write that numerator sine over denominator cos. Multiply, here's your cos x up here. And cosecant is 1 over sine x. If we're dividing by 1 over sine x, that's the same as, and let's just take care of this for a second. Boom, cos x. This 1 over sine x in the denominator means that we have sine squared x is equal to the right side. Left side equals right side. And we're done. We have cos in the denominator, we have sine in the denominator. X cannot equal 10 pi over 2. That is the ugliest squirrely bracket ever. All right, last one. Now, this one looks like a bit of a schmoz, and it kind of is. So we will need some patience with this. We're going to need some room with this. Left side is 1 over tan squared a. It's 1 over cos squared a. Right side is tan squared a. 1 over sine a squared, sorry. All right. Both of these sides look ugly. We're probably going to work with each of them to kind of try to simplify them down. And so what do we get here? 1 over tan squared, remember, is cos squared over sine squared. I'm going to leave a little bit of room here. Cos squared a. I'm going to leave a little bit of room in there so I can drop in some multiplying by 1 so we can get my common denominators the same. This first factor needs a factor of cos squared over cos squared. This next piece needs a factor of sine squared over sine squared. Now we have a common denominator. And ends up being equal to 4a sine squared a over cos squared sine squared. Wow. A little tricky to see where to go from here. But this ends up being kind of a handy thing to do. So bear with me for a second. I'm going to break cos to the 4 apart into cos squared times cos squared. So I just broke that apart into cos squared times cos squared. One of those I'm going to call 1 minus sine squared. Let's see what cos squared is. Now, the reason that we're doing this is not going to be immediately apparent, but if I distribute this is cos squared a plus cos squared a sine squared a sine squared A. Just by distributing this co-squared into this bracket. This is all still being divided by cos squared A, sine squared A. Minus, right there, that's got to be a minus sign, I think, right? Because it's cos squared times negative sine squared, so let's make that minus. Right? Now, the thing to realize here is that we've got this cos squared A, and we're adding sine squared A. So those two things together are just 1. 1 minus cos squared A sine squared A all over cos squared A sine squared A. Holy cow. So at this point, it's not necessarily clear of where, if we're any further along. Sure, we have it as one expression instead of two separate fractions, but it sure isn't pretty, and we can't seem to necessarily simplify that any further. I suppose we could difference the squares, that numerator. Let's just leave it for a second, and let's work with the right side and see if we can get anywhere with this. So let's work with tan squared plus 1 over sine squared. Probably a good first step is to that tan into sine over cos. Again, let's leave some room so we can get our common denominators. Let's multiply this one by sine squared. This one over here we're multiplying by cos squared A over cos squared A. And now we kind of have a similar thing. We've got sine to the 4A plus cos squared A over cos squared sine squared. All right, now at this point, remember our second strategy is keep your eyes on the prize. Make sure you're having a look over at the other side to see what you're aiming for. And at this point, hopefully we can notice that this denominator and this denominator are the same. So we should be good with working from with the denominator pieces. Let's not adjust that anymore. And let's see what we can do with this numerator to make it look like the other one. And we have a similar problem that we had before. Here we had cos to the 4a. Now we have sine to the 4a. So let's do the same thing and break that apart into sine squared a, sine squared a, plus cos squared a. And let's see what happens. This is all over, of course, cos squared a, sine squared a. We are going to replace sine squared, one of those, with 1 minus cos squared a. And again, if we distribute, this ends up being sine squared a minus cos squared a sine squared a plus cos squared a all over cos squared a sine squared a. And if we have a look to see what we did over on the right, and we realize that this sine squared plus this cos squared, that's just 1. We get 1 minus cos squared a sine squared a over cos squared a sine squared a equals left side. Therefore, LS equals RS. Woo! There is a lot going on there. There's not necessarily just one way to do any proof. There are different ways of getting there, and perhaps there's a solution to this one that ends up being maybe a little slicker. Um, and if you, and that's fine. That's great. If you get there a different way, um, then that works. In this case, not really pretty, but we got there anyway. So this is kind of the end of this idea of proving trig identities. Now that's all left to do is your practice question. So good luck in there. If you have any questions, please let me know.